Scene script: picture this: a spaceship, filled to the brim with explosives or nuclear bombs, plunges into the heart of a black hole. What happens next? Black holes, the enigmatic behemoths of the cosmos, have long intrigued and puzzled scientists. Born from the remnants of collapsed stars, they wield a gravitational pull so intense that nothing, not even light, can escape their clutch. Shrouded in mystery, they are the perfect subjects for our hypothetical exploration today. Now imagine if we could send a spaceship, laden with explosives, straight into the gaping maw of one of these cosmic giants. An explosion of astronomical proportions ensues. But what effect would this have on the black hole itself? Would it simply absorb the energy, its mass increasing in the process? Or might it trigger a reaction far more extraordinary, altering the very fabric of the black hole's event horizon? Would the black hole simply swallow the explosion, or would something far more fascinating occur? It's time to dive into this cosmic conundrum. First, let's blow things up, quite literally. Now imagine we've managed to send a spaceship loaded with nuclear bombs into a black hole. What would happen if we detonated them? To understand this, we need to delve into the core principles of nuclear fission and fusion. Nuclear fission is a reaction in which a heavy nucleus splits spontaneously or on impact with another particle, with the release of energy. This is the principle behind the devastating power of atomic bombs. On the other hand, nuclear fusion is a reaction in which two or more atomic nuclei come together to form one or more different atomic nuclei and subatomic particles like protons or neutrons. This difference in mass between the reactants and products is manifested as the release of large amounts of energy. This is the process that powers our sun and other stars. So we've got our spaceship inside a black hole, and boom, we trigger a nuclear explosion. But here's the catch. Black holes, as their name suggests, are places where gravity is so strong that nothing, not even light, can escape. So when our spaceship explodes, all the energy released, whether as light, heat, or radiation, cannot escape the black hole's gravitational pull. Now, according to Einstein's famous equation, E equals mc2, energy and mass are interchangeable. This means that any energy trapped inside the black hole will effectively add to its mass. So, counterintuitively, our explosion would not destroy the black hole, but instead, it might make it even bigger. Remember, black holes aren't just holes in space. They are massive objects with incredibly strong gravitational fields. Theoretically, even throwing in a bunch of antimatter or trying to spin the black hole faster to make its event horizon disappear would not work, as the black hole would simply absorb the energy and increase its mass. But the question remains, would this colossal explosion have any effect on the black hole? Well, we're just getting started with our cosmic experiment. So, stick around as we delve deeper into the mysteries of black holes in the next scenes. Welcome to the Energy Mass Exchange Program, where E equals mc squared. This equation, famous for its simplicity and profound implications, ties two seemingly unrelated concepts together: energy and mass. Albert Einstein, the father of this theory, showed us that mass and energy are two sides of the same coin. Let's delve a little deeper. The E stands for energy, m for mass, and c squared is the speed of light squared, a constant. This equation suggests that energy can be converted into mass and vice versa. It's the fundamental principle that powers our sun and other stars, where the mass of hydrogen atoms is converted into energy through nuclear fusion. Now imagine if we detonate a nuclear bomb inside a black hole. The explosion would release an enormous amount of energy. According to E equals mc squared, that energy has a mass equivalent. This means, instead of reducing the black hole's mass, we might inadvertently increase it. Here's why. Black holes are notorious for their insatiable appetite for everything, even light. When a nuclear bomb explodes, it releases energy in the form of light and heat. The black hole would gobble up this energy, and given its mass equivalent, the black hole's mass would increase, contrary to our initial objective. So the destructive force of our nuclear bomb turns out to be a productive force for the black hole, making it even more potent and dangerous. Quite ironic, isn't it? The Energy Mass Exchange Program shows us that the universe operates on principles that are far from intuitive. Things that seem destructive in our everyday life could be constructive in the bizarre realm of black holes. It's a mind-bending concept that challenges our conventional wisdom and keeps us humble in the face of the vast, mysterious cosmos. So, a nuclear explosion might not be the solution, but what about antimatter? Let's explore this tantalizing possibility in the next scene. Brace yourselves, because it's going to be a wild ride into the heart of a black hole. Enter antimatter, the bizarro twin of matter. Now this isn't some sci-fi jargon or a comic book concept, it's very much real and very much fascinating. Picture every particle of matter having an evil twin with an opposite charge. That's antimatter for you. But here's the interesting part. When matter and antimatter meet, they annihilate each other in a burst of energy. Yes, you heard that right. Complete and utter annihilation. That's why we don't find antimatter lying around. It's too busy getting into fights with matter and, well, exploding. Now let's get to the juicy part. Theoretically speaking, if we were to create an antimatter bomb and throw it into a black hole, what would happen? Would the antimatter annihilate the black hole's matter? Would the black hole simply swallow the explosion and ask for seconds? Well, the answer isn't a straightforward one. Some theories suggest that an antimatter explosion might disrupt the event horizon, that point of no return around a black hole. The energy released from the antimatter-matter annihilation could, theoretically, create enough outward pressure to offset the inward pull of the black hole's gravity, at least temporarily disrupting the event horizon. But, and there's always a but, this is all speculative. We don't have definitive answers. Antimatter is incredibly difficult to produce and contain, let alone in quantities sufficient for an explosion capable of disrupting a black hole. Moreover, even if we did manage such a feat, it's uncertain whether the energy released would indeed disrupt the event horizon, or simply add to the mass of the black hole, making it even more voracious. After all, energy and mass are two sides of the same coin in the universe's economy, thanks to our friend Einstein and his famous equation, E=mc2. Intriguing, isn't it? But there's more. What if the black hole itself could be the key to its own destruction? Stay tuned as we dive deeper into the enigma that is the black hole. Black holes, they're not just space vacuums, they also love to spin. Now let's talk about the waltzing world of black holes. Just like the Earth spins on its axis, black holes do too. This spinning is known as rotation, and it's not just a trivial characteristic. It might be the key to understanding how we could potentially make a black hole's event horizon disappear. You see, as a black hole spins, it drags spacetime along with it, an effect known as frame dragging. This causes the creation of an outer region, the ergosphere, where objects can theoretically exist without being sucked into the black hole. However, it's when we delve into the rotational energy of a black hole that things start to get really interesting. The rotational energy of a black hole is massive, so much so that it can be tapped into. The Penrose process, named after the brilliant mathematician Roger Penrose, posits a scenario where an object falling into the ergosphere could split into two. One part falls into the black hole, decreasing its angular momentum, while the other is flung out with more energy than it started with. Essentially, the black hole is forced to give up some of its rotational energy. Now imagine if we could repeat this process over and over again. Theoretically, it's possible to decrease the black hole's angular momentum to zero, causing the event horizon to shrink and ultimately disappear. If this happens, any objects trapped near the black hole could be freed. Of course, this is all theoretical. We're still a long way from even getting close to a black hole, let alone manipulating its rotation. But isn't it intriguing to think that these cosmic devourers of light and matter might have an Achilles heel? So, it seems the black hole has its own self-destruct button, doesn't it? We've navigated through explosions, energy, antimatter, and rotation, but where does that leave us? As we've journeyed through the cosmos, we've discovered that sending a spaceship filled with explosives into a black hole would merely increase its mass due to the energy-mass exchange. Even the enigmatic antimatter, a substance of contradictions, wouldn't dissolve the event horizon as one might initially assume. Instead, it would simply add to the black hole's mass like ordinary matter. We've also dabbled in the realm of rotation, exploring the idea that a spinning black hole might somehow make its event horizon disappear. But alas, this too proved to be a cosmic curveball. So as we've discovered, destroying a black hole isn't as simple as it sounds, but isn't that what makes the universe such an intriguing place to explore? Join us next time on Nebula Narratives, where we continue to unravel the mysteries of the cosmos. Don't forget to subscribe.